If a glass plate with index of 1.56 is 15 centimeters thick, what is the lateral displacement for a ray incident at 45 degrees? So we're told that this thickness is 15 centimeters, the distance between the incident interface and the emergent interface. And the index of refraction is 1.56. And if we were to draw in a normal, we know that the incident angle is 45 degrees. That's here. And to find the lateral displacement, we can use the equation d equals t, meaning the thickness, times the sine of theta 1 minus theta 1 prime divided by the cosine of theta 1 prime. And we are given the thickness, we are given theta 1, so we need to determine theta 1 prime before we can find the lateral displacement. For that, we'll use Snell's law. And our incident n, we're going to assume is air, so index of refraction of 1 times the sine of 45 is equal to n prime, which is the glass, 1.56, times the sine of theta 1 prime. And here we find that theta 1 prime is equal to 26.95 degrees. On our diagram, that would be the angle right here. And now we can plug in theta 1 prime along with the other variables into our equation. So d is equal to the thickness, we'll just use centimeters, 15 times the sine of theta 1 is 45, minus theta 1 prime is 26.95, and divided by the cosine of 26.95, and we come up with the distance is equal to 5.21 centimeters. So that d is our lateral displacement, and we could draw that on here. We would assume that this, we'll extend our interface here, and this ray would then be refracted going from a high to a low index, would be refracted away from the normal. Like this, if we had a normal drawn in right here. And so the lateral displacement would be the distance between where the original incident ray was going, so we could extend that as a dashed line, and then where the actual emergent ray actually ended up going. And this distance, the perpendicular distance between those two lines, is your d, the lateral displacement. So that in this case would be 5.21 centimeters.